multi-vibrators and so-called IC 555. Okay, so now I think we should start because others have not come. That means them I made some contingency plan for them. So let us start. I take the presentation in my hand and then I will correlate the previous lecture with today's lectures. Okay. I will be considering the case of proper design, not that direct coupled multi vibrator or something like that. Direct couple I have already explained what are the drawbacks, etc. And you already know that other improved designs I have given, and based on that I am going. So I will start with the improved design in which the self-biasing is not there, and I will complete my monostable astable with that concept. Later on, similar thing, when the self-biasing is there, emitter is elevated from the ground, then what is happening in monostable and astable, we'll see that. Okay, the range of the fluctuation will be somewhat controlled by this putting on emitter bias, or you can say self bias. And similarly, the emitter coupled circuits, which was Smith trigger in case of bistable multi-vibrator, it can also be biased as monostable multi-vibrator and an oscillator, that is your astable multi-vibrator. So 555 timer is very often used as oscillator, as a timer, clock generator. Okay, so I'm just drawing the circuit where I said that some improved design of the bistable multi-vibrator. I give a mail to you that file. I posted it, uploaded it in that general section. Okay, so I'm here. What did I do? This was the binary bistable multi-vibrator. This portion I grounded, and this NOT gate again I got this. This portion I grounded. Then I coupled the emitter with the base. This was coupled like this, and it was connected to the base. And here again same thing, through a resistance. This was coupled to this base. This was my VCC. You remember the circuit? This was the one I made. Then how to bring one of them in saturation, one of them in cutoff, and not too much in the saturation. Cutoff it can go too much, no problem. But saturation it should not go in deep saturation. So what do? I connect a resistance here. I connect a resistance here, and here I give a negative supply, VVB. Names I gave are RC, both of them I put as RC. This was my R1, this was also my R1, this was my R2, this was also my R2. So symmetric circuit I made, I'm gone by that. When I come, this is your minus VB, sorry, here is the minus 1, the minus VB. When I come to the monostable, one of this thing will be disconnected from here, and this one will be given to positive supply. I'll make the circuit like that. It will be given to the positive supply, and this resistance, one of them, will be cut, and a capacitor will be put in that. So one collector is coupled to the base by a capacitor, Another is coupled to the second base by resistance, and now one resistance that was going there, the negative, it remains as such. This goes to the positive, and convention is that this one I make initially at t equal to infinity as on, and this one I will design as off. So this positive supply, I'll put it nothing but same thing as my VCC. Okay, so one of the resistance is going to VCC, and at that base a capacitive coupling is there of the collector. This becomes the monostable multiplier. I draw a better diagram now. Now you see the changes that I'm going to make. So this is my monostable, this is my RC. This is the emitter, is going to the ground. Here I am putting a resistance. This was going to the base of this transistor. It was coming like that. Now at this base, okay, I was making a resistance going to minus VBB, that I am changing. So in here and here it is same thing. I am putting a resistance here going to VCC directly. So this is my RC. This is also my RC. This is I'm calling as my, what you call it here, I used to call as R, isn't it? R2 and R2. This I am putting as R because it's not no longer remaining symmetric. Here is my R1 and it is going to the second base where I'm using a negative bias here, minus VBB through a resistance R2. This is because I want this one to be driven deep into cutoff, but I want that this should not go deep into saturation, otherwise it will lead to the delay. And my initial biasing will be, when I switch on the circuit, I consider that is t equal to infinite. T equal to 0 I will consider for the capacitor what is going to have. When I switch on the circuit, I will start my experiment after a few seconds, but this circuit working in milliseconds. So when I say t equal to infinity, implies, what is that? VC2 collector the second transistor. I'm calling this as my Q2. I'm calling this as my Q1. So VC2 is nothing but VCES at t equal to infinity. Okay, I'll come to t equal to 0 plus and some other intermediate time in between to solve that. VC2 is VCES. What is my VB2? It has to be greater than or equal to V sigma. So VB2 at t equal to infinity is greater than equal to V sigma. So Q2 is in saturation, not much larger than V sigma, otherwise it's deep into saturation. That we want to avoid by putting the resistance, this R, connected to this VCG supply. Okay, now at t equal to infinity, what is my VC1? This one is cut off state. So this was on, this was my off. So VC1 is what? VCC. And what is my VB1? VB1 has to be less than or equal to V gamma. I want to make it cut off. And accordingly, I am putting what is the value of VB1? Current comes from VCC to minus VBB via this RC, R1 and R2. So this one will be VB1 will be nothing but VCC plus VBB, because VCC minus VBB, V my negative, so becomes a plus, divided by R1 plus R2 plus RC. Plus RC is the current, this into R2. And this equation I have to solve so that this becomes smaller than V gamma. Okay? It can be negative also. Even if it is negative, accept it. Otherwise, in positive direction, it has to be V gamma or less than that. So that way, I am finding, with the help of VBB and VCC, I am finding R1, R2 and RC according to that. Okay? Coming to this, this was your VC2 is VCES, VB2 is greater than V sigma when I say, what is my VB2 at this point? My VB2 at this point is what? VCC, this is nothing but, VB2 is what? VCC minus V sigma, or you can say VB2, whatever is there. VCC minus VB2 divided by R is the current. Okay? This current is coming here. It is just like VB2 only. This equation I did not write. This into R is my VB2, so it is VB2 as it is. VB2 voltage that is coming here, it has to be greater than V sigma. And how much is voltage coming? VCC into IB on current. That means here I can write here VCC minus IB on, which can drive it to saturation, into R. That is my VB2, and that has to be greater than V sigma. So IB on, I had to take from the manufacturer's data how much current should be flowing through this to make it on state, but not in the deep saturation. So that way I have calculated what is the value of my R. Now see, I can put anything arbitrarily. R is the something that is constrained to the design to make it on and off according to that. So that way R is coming. C I am free to choose anything. So R and C I have put over here. Is it clear? Monostable multivibrator is designed like that. How does it work? I am going to explain. Any question here? Question? Okay. What will be the charge on the, what way the capacitor will be charged? Initially this is your VCC. T equal to infinity, it is VCC. Here it is VCC coming to this through this R. What is the voltage here? IB on into R subtracted from VCC, that is this thing. This is your VB2. What you have taken in the saturation, that voltage comes here. Okay? Now capacitor will start charging when? Now I have to bring the concept of T equal to 0 plus. T equal to infinity is something like T equal to 0 minus, you can say. It resembles T equal to infinity. T equal to minus, sorry. T equal to 0 minus, it resembles T equal to infinity. Case. Now I'm going to define T equal to 0 plus and T equal to capital T. What is going to happen at this capital T? That I'm going to fix it according to my capacitor. Is it okay now? So t equal to infinity I have solved. I have designed the circuit. It will get some disturbance of electrical noise or so, and Q2 will go to saturation, Q1 will go to cutoff. It will start for operation from that particular state. Shall I go ahead now? Students are not responding. Seems they understand it. Okay. Can you hear me, by the way, all of you?
Yes, sir.
Okay, it's fine. Now I'm coming to this point. What I have drawn there, this circuit I'm putting here as my VC1. It is VCC initially. It is connected to this VCC through this RC. Okay? And this was going to the base of this thing. A capacitor was here. There was a resistance here. As I said, you can trigger the multi-vibrator with a positive pulse, with a negative pulse both. Okay? I have put this as R. This is my C. Okay? And this side, same thing, RC is coming as same. This R is coming here. And this R goes to this base, and here minus VBB is given. And here is my emitter. Going as it is. At this base, this resistance goes to your positive supply. So it has come like this. And this positive supply I'm putting as VCC. The single supply I am using in the RC and R connections. Here, second supply I am using for controlling my saturation and cutoff states like that. This was the thing. Now at t equal to 0 plus, I apply a impulse here at this base. Okay? I can say trigger. Trigger is narrow pulse. Trigger is applied to base of the second transistor. I'm calling it as base of the first transistor. Positive trigger. Trigger which is positive. I'm putting here as positive. Negative trigger I have to put at the base of the second transistor. Okay. So this is my Q1. This is my Q2. Now a positive trigger I have applied to the base of view. As a result, what happens? A current will flow through this resistance RC. This current. Earlier current was not flowing. This was VCC. This was VCC. No current was flowing. This was a capacitor here. So t equal to infinity, nothing was there. Now it has become VCC. So what you are having? VC1 becomes, it was earlier VCC minus drop I1 into RC. I call this current as I1. I1 into RC. So it becomes VCC minus I1 into RC. Okay, that will be my VC1. And the same voltage, this voltage, will come at the base immediately because capacitor is not having any charge. So no charge. No charge at C, okay, gives BV2 becoming equal to, that was V sigma, whatever are there, minus I1 RC. Same thing comes here, translates. So what is my VC2? At 0 plus, remember, t equal to 0 plus I'm talking. I have not gone ahead now. At t equal to 0 plus, what is going to be my VC2? VC2 will be how much? VCC plus VBB divided by RC plus R1 plus R2 into RC. Okay, so VC2 will be VCC divided by VCC plus VBB rather divided by R1 plus R2 and of course RC is there. Coming from the collector of the second transistor, remember. Into what? This is this voltage I want to find. So if make it R1 plus R2, that will be the same as if I make it into RC, because the RC is also getting rounded rather. Anyway, let me put R1 plus R2 here, doesn't matter. I can put it here R1 plus R2. R1 plus R2. So this becomes my VC2 at t equal to 0 plus. Now I am interested in knowing what way the capacitor is charging and the voltage at B2 is changing. See, VCC plus VB2 divided by like that, this will be approximately equal to VCC. This will be approximately equal to VCC. You can work out for any practical value of R1, R2 and RC like that. This will be approximately equal to VCC. Now, VCC I'm not that VC2 I'm not that much bothered because it is too high, so it will remain in cutoff only. I am bothered about VB2 at some time t, not t equal to 0, t equal to infinity, not. So VB2, and you remember to represent that with the capacitor is there, so exponential term is there. There can be some constant terms also. I have to evaluate those constant terms. So I write it. Remember my first lecture on your capacitor charging discharging only. Remember that. I can write here A plus B e to the power minus t by tau. Okay. Now you remember when I wrote at that time VB2 at 0 plus at 0. Okay, is how much? A plus B. E to the power 0 becomes your 1. Then I can write here VB2 infinity, final one will be what? This will be your A. I can say this is my VB2 initial value and this is my VB2 or V output, you can say final value. So initial value and final value will give me the values of A and B. Okay, so I can write the voltage coming at my base of the second transistor changing with time in this form. I can write here for your sake of continuity. I'm writing because I already have done that. I'm repeating the same again. VB2 as a function of time is nothing but, here I can say A, that is VB2F, that is my A. Okay, then I want to find my B. So this minus this. So VB2I minus VB2F. Okay, VB2F. Here will be my VB2I minus VB2F. Okay, into e to the power minus t by tau. Anybody who has got doubt or some sort of suggestion can tell me. It will be nothing but VB to the VB to F plus this initial minus final e to the power minus t by tau. So you can find the, voltage across the capacitor, etc. You can solve by this method also. Now I will start my talk with this value now. Now what the potential varying at the base of B? When this base of B2 of second transistor will drive it into saturation, that point I am interested because it has come back to its own stable state. Here, given the impulse is gone. So it is on a stable state, e to the minus t by tau is increasing the voltage here. Earlier it was VCC minus I1 RC. So now, V sigma minus I1 RC. V sigma minus I1 RC. Now it starts growing slowly, exponentially with this equation. Okay? Shall I write the value and then I go to the next page? That is better then. I can write here VB2 is nothing but, what is my V2F? T equal to infinity. T equal to infinity, remember? Where is that? No charge C, VB2 so and so. T equal to infinity. I've got how much? Let me put here. T equal to infinity, it was on state, okay? It was on state. So VB2 final is nothing but, I can say, V sigma, something close to that, V sigma dash. Because it was in the saturation, not exactly at the border of saturation, it was inside the saturation. V2 was V sigma, it was VB2F. And VB2I was what? VB2I. That was what? Initially, VB2F, finally it was saturation. VB2I means when T is applied. Okay, so it was your this thing, VCC minus ICR1. VCC minus I1 RC. Okay, agree to this or not? At T equal to 0 plus, either the trigger was applied, this became what? VCC minus I1 RC, that drop. Same thing came here also, VCC minus V sigma minus I1 RC. So it is V sigma, I always make this V sigma or V sigma dash, whatever you say, V sigma dash minus I1 RC. So V2I V sigma dash minus I1 RC, V2F is your V sigma dash. Now I write the equation and I have got a very beautiful equation. I can get the solution quickly. Shall I proceed? Anybody is needing any kind of input here? Okay, I will start from this point. I will write it now. So I have got here VB2 T. Now I'm writing here. Can I write it like that? VCC minus VCC minus V sigma dash minus VCES. No, VC2 will be like that. Sorry, 1 second. Yeah, VB2 will be. Let me use one more. Okay, I can put here. VCES what is this? VCC minus VCES, okay, is equivalent to I1RC. That by that there was a drop. This is nothing but I1RC. There negative sign here. Okay, it was dropped by that. So it is your how to say that? I think I write one more step, then it will become clear. Let me write one more step, okay? BB to T is nothing but intermediate step. I should not remove, otherwise you will be BB to F. That was your VCC. BB to F was VCC 1, VC1 final F. Remember that? This is my VC1. It was coming through a capacitor and coming to this B2. So what was this final? This voltage and this voltage is the same. And at infinity, this becomes cut off, so it is VCC. Okay? So it is your VCC and this thing VCC, this final comes at this point also. So same thing comes over here. Voltage is the same. This is really transfer. That is the VCC is a V2F final. Okay? Minus initial voltage VCC minus V sigma. This was F. This was the initial voltage. Okay. VCC. Where is the mistake? VCC minus V sigma plus I1RC, and I1RC is what? Let me put right here that. Here I have got VCC plus V sigma minus I1RC. That was my final. Okay. I1RC plus VCC e to the power minus T by tau. Tau calculation will come later on. What is this? This is my VI, okay, minus VF or VCC. So there has to be a minus sign here, no? What is that? There has to be minus sign here. What's the VC? This is VC1 rather. V0 minus IRC. I1RC. V2F is how much? Is it not VCC? Is it VCC only? It is VCC only. So this is VCC. It's okay. This VCC is VB2F. This is VB2F. Okay. But there has to be a negative sign there. VB2F would come as a negative. And VB2F is coming as VCC. So that becomes your minus VCC. Yeah, it's okay. This is your V sigma I1RC minus VCC. It's okay. This is minus VCC. It's okay, fine. Is it okay? VCC plus V sigma minus I1RC minus VCC. This is a VF e to the minus T by tau. I'm writing like that. This is my this thing. Now I can write here. Here I am putting as VCC as it is. I can take minus outside common. So this becomes your VCC, minus becomes plus, V sigma becomes your minus, and plus I1 RC. Manipulation, nothing else. E to the power minus T by tau. Tau will be RC. What is the value of R? I will come to that. Tau will be RC, R into C. This is your E to the power minus tau into RC. Now this is the thing. What is my I1 RC? It is flowing in at T equal to 0 plus it flew, we can say, it flew in this Q1 transistors collector arm. Okay. So at that time, what was the I1 RC? What was that? T equal to 0 plus. This was the final when this was applied there. This was in saturation. Okay, this went in saturation at that time. So T equal to 0 plus. It was your VCC minus VCC minus V sigma, and this was nothing but VCC minus VCES. Because collector emitter became saturated when the trigger was applied, so it was VCC minus VCS was I1 RC. I1 RC is not changing, remember. I1 RC was the initial time when I got it, and at that time T equal to 0 plus, this went into saturation. This is for the Q1. Q1 went into saturation. VCC minus VCES is coming like that, and this thing into E to the power minus T by tau. Now it's okay. I can write it now. This is nothing but VB2T is nothing but, here is my VCC, minus I'm taking here, this will become 2 VCC, this plus this VCC, 2 VCC, minus V sigma, minus VCES. Okay, into E to the power minus T by tau. Okay, now I can go for the manipulation. I create a room here itself. You should not be having trouble in understanding that. I am erasing this portion. I'm making room here, okay? I'll be changing the color of the ink also for your convenience when I start writing here, because black and red can be discriminated very easily. Yeah, here I'm using the red ink to write the final result, etc. I'm choosing the red here. It is not selected. Color 1, it should change. Now it has become red. Okay, fine. So why is my VB2T? This is my VC. Oh. Edit colors, okay. It's not, oh, eraser I have to remove, sorry. I have to choose the pen. Okay. Now it is red, it's fine. Now VB2 is nothing but, here is my VCC. I take 2 common here. This becomes your VCC minus V sigma plus VCE bracket divided by 2. I've taken 2 common. E to the power minus T by tau. Okay. Now I have written like this. So what is this? VB2 becomes my, it is going to cross the V gamma, that means second transistor becomes active. So it should be V gamma or more than V gamma. So when it becomes V gamma, at that particular time, I'm taking my time threshold in which I'm interested. It can be more than V gamma. I'll be going for that, V gamma or more. So when it is going V gamma, VB2 will be nothing but VCC, because when we cross a V gamma, it will start conducting. Earlier it was off. When T equal to 0 plus, trigger was added, that was off. So V gamma is your VCC minus 2 into VCC minus, I can approximate V gamma plus VCE divided by 2, this average as very close to V gamma. This can be approximated. And e to the power minus t by tau. Closely it is approximated. This average is coming close to your V gamma. Okay, I can put V gamma dash, it's close to that. So VCC minus V gamma will be 2 into this thing. So what is my t? You can know, you know how to. This is happening at t equal to capital T, not at this one. T equal to some capital T, it has happened, it has become V gamma. So your capital T will be nothing but this tau logarithm 2, because of this 2, this tau is coming as a multiplier there, okay, plus tau into logarithm of VCC minus V gamma dash divided by VCC minus V gamma. And this becomes your 1. Logarithm of 1 becomes your 0. So this term becomes your 0. So your t has become equal to, approximately equal to 0.69 tau. And what is my tau? Here is my VCC. Here is my R. Here is my C. Here is my RC1 Thevenin's equivalent resistance, and here is the VC1 Thevenin's equivalent voltage. So it will be DC only, so it will be a plus, minus like that. So from here, this was my R. So it is charging through a current, okay, and that is passing through this R plus R C1TH and C. So your tau is nothing but R plus R C1 Thevenin's equivalent resistance into C, and this T is the width of the pulse during which your Q1 was off and Q1 was on and Q2 was off. At this point, Q1 becomes off, okay, and Q2 becomes on. So becomes on means this is nothing but a VCES. And this is approximately equal to VCC. This is your capital T. So it will start coming like that. What will be this portion? This portion will be when the trigger is applied. Okay, period of trigger, TP. On the pulse, trigger pulse we are applying, that time period will give you this thing. So this one will be TP minus T. So T you have computed 0.69 into tau, and for your another approximation, RC1 Thevenin's equivalent is very small compared to this R. So you can make this as tau equal to RC. Because the way you are chosen your RC and all that and saturation etc., your RC1 Thevenin's equivalent is very small compared to R. So R plus RTH is approximately equal to R. So tau becomes equal to, sorry, T becomes tau becomes equal to RC. Tau becomes equal to R into C. Tau becomes equal to R into C. So this becoming equal to 0.69 RC. So width of the pulse during which the flip-flop is changing the state, that will given by 0.69 into R into C. Which R? That was connected from the base of second transistor to VCC. That R, it was connected to the capacitor also at the same end. So that way I can design what should be the width of it. Any question? Formula has come in the form of 0.69 RC. And this is the same thing giving you a kind of input to a stable multi-vibrator. What is that? A stable multi-vibrator, you make two monostables connected. Your bistable part is gone, totally gone. So what we write here for A stable multi-vibrator? This is this RC. This is this. It goes to the ground. This is my base. This is my capacitor. This is my resistance. RC. This R and C. This is your RC. Now this is the second transistor. Grounded here. This is the base. Here again I am putting a capacitor. So two monostables are now connected back to back. Now just see that stable part is gone. This switch connected to this. This is connected to this, and this base is also connected to VCC only. So this is your R. This is your RC. This is your C. So symmetric circuit. This is my VCC. So what happens? It will automatically switch from on to off state for both the transistors. And what will be the width? From here to here, it will be your 0.69 R1 C1. I'm calling this as R1 and C1. This will become my T1. This thing and this thing will be something. It will remain here. This will become on. At that time, what will be there? 0.69 R2 C2. This is my R2. This is my C2. It will be charging like that. From here it was charging like this. Now here it is charging like this with VCC, coming out to this VCES. So that way the same thing applies there. That becomes your T2. So your pulse generated will be something like that. This one will be your T1. This one will be your T2. So no trigger is required. Automatically it is switching on and off. Initially some noise has made the provision to go with this one into saturation, any one of them. And after that it starts oscillating. And what is the time period of this oscillation? T1 plus T2. I'm calling it as time period T0. So what is the frequency? F naught is 1 by T0 hertz. If T0 is in seconds, 1 by t naught second becomes your hertz. So that way the oscillation frequency and the even duty cycle, if you want, you can control that in a stable multivibrator. This is a stable. Okay, so I stop it here. If there is a question, I welcome. 5 minutes before I'm leaving because I'm supposed to finish 10 minutes before, but anyway, I will take an extra 5 minutes. If it is useful to you, I'm happy. Any question? Monostable multivibrator and astable multivibrator I have covered today. But remember, I have done only for collector coupled case, not for the Smith trigger emitter coupled case, which I have done for the bistable case. These two are possible for emitter coupled cases also, and that will be once again, I mean, easy to design using the your 555 timer or even Smith trigger that you have made as a circuit in your lab yourself. Shall I stop it here, friends? Any question? Strength is very few. By your such a weekend, I mean, programs will be coming in this winter semester. I have heard that even a couple of times more. But we have to finish our things in the stipulated time. Semester cannot be extended. That's why the instruction of the registry we have to follow. Exactly according to that, we have to do that. Your friends can exchange notes with them. This I have not uploaded because this was more of a discussion kind rather than conceptual talking or so. That V output equal to A plus B e to the power minus t by tau. That is the thing that you must remember, and I think that you have done in your some of the, if you JE also, I think you must have prepared like that, because the voltage capacitor is calculated by using that VI and VF, V initial value of the output, final value of the output. Based on that, I can find what is going to be V naught at a particular time t. Anyway, so that has to be considered here. I close it here. Monday, I think as per the notice, am I correct? Your class will be not there. Am I correct? Anybody can correct me. Monday after
Yes,
3
sir. Classes
o'clock.
from 3 p.m. are not
exactly.
held.
So your class, I think, will be off on Monday, and yeah, that's why I have postponed your quiz 3 exam to 7th of March, because 3rd and 4th I will be talking for the tutorial that way. Because Monday I'm losing, so I have to go by that. Okay. So I think Professor Sen Gupta will mail to students about the quiz 3 exam dates.
Yes,
maybe Tuesday or Wednesday, that they should be knowing about. Okay then.
okay,
Good
sir.
day. See you again.